Welcome to the Henry AI Labs walkthrough of Keras code examples. Keras has provided 56 code examples implementing popular ideas in deep learning. This ranges from the basics such as simple MNIST and IMDb text classification, all the way to cutting-edge research ideas such as knowledge distillation, supervised contrastive learning, and transformers. We'll also explore fun generative examples like variational autoencoders and CycleGAN. My contribution to these code examples is to explain every single line of code in each of them, walking through each of the individual Keras examples. I'm not the author of these code examples. Please consider starring the GitHub repositories to show support to the original authors. This next Keras code example will explain few-shot learning with Reptile. Reptile is an approximation on the model-agnostic meta-learning algorithm that avoids having to do this gradient through a gradient outer-inner loop optimization thing. Reptile is rather going to simplify the problem by just having this update where you have an initial set of parameters, then you go learn a new task in the few-shot learning sense, and then you take the difference between the parameters that were learned with that new task and the original parameters, rather than actually taking the derivative with respect to the initial parameters. So it's a simplification of this problem of outer-inner loop gradient descent learning, but it does work pretty well, and we're going to see this application in few-shot learning with the Omniglot dataset. This Keras code example implements Reptile. Reptile was proposed in this research paper from OpenAI on first-order meta-learning algorithms. Particularly, it's a simplification of this MAML algorithm, as stated here, by ignoring second-order derivatives. And MAML is this paper, model-agnostic meta-learning for fast adaptation of deep networks. So this diagram depicts what we're trying to do well. We have an initial set of parameters, theta, and now we're deploying those initial parameters into a new classification task that we've never learned before, shown here as L1, L2, L3, and we're trying to learn how to do these different tasks without a lot of data. And the idea is that having a good set of initial parameters will help us learn this task faster. So in MAML, they take the derivative with respect to this new task, also with respect to the parameters of the initial network, whereas in this simplification in Reptile, we're just going to update the parameters in the direction of this new task and just kind of play it like that. So we have a new task and we're going to shift the parameters a little bit towards that direction and so on to try to learn these different subset samples of the Omniglot dataset. So this idea of trying to learn an optimal set of initial parameters that can quickly learn new tasks is a really exciting paradigm of deep learning. We've seen things like GPT-3 that can learn these new tasks really quickly, even without any gradient fine-tuning. We've also seen things like pattern exploiting training that shows further ideas of how to realize this idea of few-shot learning. It'd be really cool to have models that can quickly learn these new tasks in this kind of similar comparison of where you compare artificial intelligence and human intelligence, and you say that humans don't need thousands and thousands of examples to learn a new task, and this is kind of one of the first steps in this direction of trying to do few-shot classification and learn tasks quickly without too much labeled data. Additionally, this paradigm of teacher-student outer-inner loop gradient learning has led to some really interesting research directions. This paper, Generative Teaching Network, has this outer-inner loop gradient where the teacher is trying to design a data set for the student to learn from. In this case, you can see the final data set produced for learning MNIST and for learning CFAR10. Another creative way of thinking about these outer-inner loop gradients, not just thinking about the initial set of parameters, but maybe also trying to learn the data set itself, which is a really ambitious idea. This other paper, Teaching with Commentaries, kind of summarizes this general research direction and many different ideas, and particularly is focused on this other idea made probably best implemented in meta pseudo labels, where you're trying to learn a shifting label distribution for the data. So three things are presented here quickly. You have the idea of learning an initial set of parameters, the idea of learning the data set itself, or an idea of learning this soft label distribution over the Y's instead of one-hot encoded vectors, sort of similar to the soft distributions produced by knowledge distillation. We try to have a teacher control these label distributions to apply density on not just the ground truth label of the object category. So this paper and this Keras code example of implementing Reptile should be a very interesting first step for you if you're curious about these kind of algorithms of this teacher-student gradient learning, and particularly this simplification of it makes it a lot easier to understand, and hopefully it still works. So it does seem to work in the, as I show in the paper, it does seem to work in the Omniglot setting and this kind of image classification setting, but it remains to be seen if it can do things like generative teaching networks and so on. But here's an interesting place to get started, and we'll walk through this example of implementing Reptile on the Omniglot dataset. The notebook begins with our standard imports, matplotlib, numpy, random, TensorFlow, Keras layers, and then TensorFlow datasets where our Omniglot dataset is stored. So now we're going to be defining some hyperparameters for our meta-learning, few-shot learning training loop. So it's important to note that we are going to be, as described here, we're going to be sampling a batch of classes, and then we're going to have a number of inner updates as we move the initial parameters towards this new sampled task. So we have these hyperparameters that define the number of meta iterations, which is overall how many of these different tasks we're going to sample from. And then we have the inner iterations, which is how many steps we're going to do within each sampled task. So this will make more sense as we go deeper into the training loop and describe it further. So next, let's describe the dataset itself, the Omniglot dataset. The Omniglot dataset is one of the most famous datasets for few-shot learning. It's very similar to the MNIST handwritten digit dataset in that we have 1,623 characters from 20 different alphabets, and we have 20 different handwritten renderings of each of these 1,623 characters. So using the data labeling platform as Amazon's Mechanical Turk, we asked 20 people to draw out each of these characters. So we have 20 different unique drawings for each of these 1,623 characters. And it doesn't really matter so much that there are 50 different alphabets, but there might be some correlations between the styles of the characters that maybe it could use for, inferring the label of each character. So the way that we learn this classification task is that we're going to sample k samples. So k is the hyperparameter. In our case, we see 5 is the hyperparameter value we're using. So that means we'd sample 5 out of our 20 instances for each characters, and then we're sampling a new classification task of n randomly chosen classes, and then in our hyperparameters, n is set to be 5. So what we're doing is we have 5 classes and 5 examples per class in this inner step of learning this new classification task. So we don't have a global set of class labels for all of the characters. So say it isn't like you sample the n classes and it would be like label 1,418, label 807, label 8, is rather you're going to be assigning new class labels for each new task. So the 5 classes that are sampled are then labeled 0, 1, 2, 3, and 4. So hopefully you understand this kind of training loop, the sampling of the new data set for doing this inner evaluation and doing this learning of few-shot learning. So we're sampling a new classification task. We have our initial set of parameters theta, and then given this new set of 5 characters and then 5 examples per each class, we do gradient descent learning, and we push the parameters along in the direction of optimizing it to perform this new classification task. So with that understood, the next step is to define our data loader. So we have a class dataset that's going to be sampling tasks from the Omniglot dataset. We have our initialization where we set the splits, we load the Omniglot dataset from our TensorFlow datasets library, and then we're going to do the extraction where we convert the image to the float32 data points, move it into grayscale, and then resize it to 28 by 28, similar to MNIST digits. So then we use ds.map, this extraction function. This is how we loop through the data and then map it by applying this function to each instance in the dataset. And we're going to convert our image to a NumPy array, the label to a string in the NumPy array, because the label is, we're not really using the original label from Omniglot. We're going to be sampling a new label, again, as defined by just the random ordering 0, 1, 2, 3, or 4, based on how it's sampled in this when we're defining each new inner loop optimization task. So this is how we pre-process this data and just get it ready for the actual logic of this, which is going to be sampling this new mini data set as we sample random sets of the characters and then assign these new labels based on the arbitrary configuration of these new classes in a new classification problem. Now we're in the meat of our dataset loading class. So first what we do is we assign this placeholder NumPy array for the labels and for the images, and we're going to be overriding this by indexing our original self.data and our original self.labels list. Well, not our self.labels. We're using this to index the data set, but we're going to be assigning new labels based on this arbitrary selection of the ordering of these newly sampled classes 0, 1, 2, 3, and 4. So the first thing we do is we're going to select these random labels by doing random.choices within our list of the different labels that we have access to, and then k is the number of classes, meaning the number of different choices to do. So we've selected 5 different global label indices for our collection of 1,623 different characters, and now we're going to use that to index the data set and write over our temporary image and labels batch for returning this mini data set for our classification problem. So we loop through the class index, class object, and enumerate label subset. So this is our label subset. We're looping through the 5 different randomly selected labels. So say we picked, again, like 8, 807, 1,413, these random indexes in our original set of 1,623 Omniglot characters. So next we might want to have further insight into how these inner loop training steps are going by assigning a test set as well for these inner loop steps. So we have the training step by selecting 5 examples for each of these sub-classification problems, and we might also want to reserve one character for doing a test loop that isn't with the the fitted parameters on the 5 examples for each of the 5 classes. We might also want to have one example from each of the 5 classes, or however many, so that we can have some proxy on the inner loop performance. So if we do the split, or if we don't do the split, that's just all that's saying. If we don't do the split, then we just overwrite our temporary images by just indexing into the original set with our index of the label subset as we're looping through the class index. And that's just how we access this data in this global NumPy array that contains all of these images that we have. So that's just how we overwrite the data with our new selection of the new images for our selected class index, as we selected randomly 5 classes, and then we loop through these classes by doing class index and enumerate label subset. So then what we do is we take this new nested data set and we assign a tf.data.dataset.from tensor slices, as we have this NumPy image array, cast it to float32 and cast our labels to integers for assigning the 0, 1, 2, 3, and 4 labels. And then we do this dataset equals dataset.shuffle.batch, and then repeat is another thing you would chain on to a tf.data object if it's going to be using the same amount of data a couple times. So in this case, we only have 25 examples, so we repeat it. It's going to see the same example multiple times. In this case, our repetitions hyperparameter is something we'll see later. It's passed in as an argument to get many data sets. So overall, this is going to return these nested data sets that we're going to be using to fit these sub-classification problems and update our global parameters by looking at the direction that each of these new subtasks pull it towards. Next up is visualizing some images from the Omniglot dataset, or visualizing some of these handwritten characters. So if you're curious about this idea, this probably communicates it a lot better. So we have 1,623 of these different handwritten characters. These are these random samples. So what we're doing here is in our block of code, we use matplotlib plt.subplots to find a 5x5 matrix of visualizing these images. Then we've already defined by using train dataset equals dataset, and actually creating an instance of this object that we defined earlier. We already had the tfds.load Omniglot, so we already have all the logic we need to get the data into this object, and we've actually defined it in this training dataset thing that we're looping through here. So in the data.keys is how we have the labeling of each of these things. So we overwrite each position in the plt.subplot, so this AB thing, as we loop through 5 and 5, going through the rows and the columns, and we sampled the next set from the train dataset loader and plot it. So back to the more conceptual idea of what is Omniglot. So we have 1,623 different characters, and what we're doing in this problem is we're sampling 5 of these different indexes, shown here is 617, 672, 325, 177, and then 247. So these are now going to be labeled as 0, 1, 2, 3, 4. And we're sampling 5 each of these. So on the Amazon Mechanical Turk platform, they were given one, maybe like a photograph picture of each of these digits, and then they drew out what it looks like. So we have some variance with respect to each of these characters. And the high-level task is we'd like the model to be able to take any of these characters and quickly learn to classify it into a new, arbitrarily construct these new alphabets with just sampling these different kind of characters and then assigning discrete labels to them. So now that we have a sense of the data set that we're going to be training with, let's get the model itself. So probably the main thing to note with this model is we don't want to have too much complexity, because we're only going to be training it on 5 characters in each inner loop. So if you have a lot of parameters, it could really easily overfit to this. So what we're doing is we're stacking these convolution, batch norm, ReLU blocks, and we do this 4 times, and then we flatten it into a vector and connect it to our 5-class classification problem in this case, because we have 5 classes, and so we do a softmax distribution over these 0, 1, 2, 3, 4 class labels. So this is how we define our model. And probably the only interesting thing to note here is it's kind of a low capacity model, because these are only 28 by 28 MNIST resolution digits, and we're only looking at 5 classes and 5 instances at each inner loop. So we don't want it to just overfit that too much, and maybe pull these gradients and pull the initial parameters in a meaningless direction because it's really just overfitted to it. Next, we're looking at the training loop itself. So this can be a little bit of a confusing thing, but it's not so bad once you just kind of separate this idea of the meta iterations and then the inner iterations. So meta iterations is describing overall how many times we're going to be updating our global initial parameters theta. This is like the product of our search, is trying to learn the best set of initial parameters for adapting quickly to learning each of these new classification tasks. So within each of these meta iterations, we're going to sample n of these inner tasks. So we described how one of these inner tasks means sampling 5 different random classes, or 5 different digits from our set of 1,623 digits, and then sampling 5 samples. These are just the hyperparameters of our algorithm, of sampling 5 different instances of each of these 5 classes. That's one inner problem within one of these meta updates, but we can adjust this to learning several tasks at once. So shown in this diagram is learning 3 different tasks at once. So, this is a hyperparameter of the algorithm, exactly how many of these sub-classification problems we want to sample from and learn in these update steps. But the meta iterations refers to how many overall times we're going to be sampling these inner problems. How many of them we're going to be sampling is another hyperparameter, and then how many gradient descent updates to make on each of these inner problems is another hyperparameter to be selecting. So, a couple things about tying this training loop together, and I hope that, communicated it well enough. So now we're in the code for actually implementing this training loop of having meta iterations and then the inner updates. So first we're going to be defining these 2 arrays to store the losses. Then we're looping through the number of meta iterations. So say we want to do this 100 times, we loop through and do it 100 times. So first we start off with the fraction done, and then we from that we derive this meta step size. So it looks like when we're doing this global update, as we're updating our global parameters in the direction of the new parameters, we're going to have this, it's just like this standard update rule if you've seen stochastic gradient descent, where it's the old parameters plus the gradient times the learning rate. So our learning rate is this the current meta step size, which is derived based on how far along in the meta iteration we are. So I think this is kind of like having a learning rate for the meta steps. So we have a learning rate on updating these parameters that it looks like it's going to be adapting over time. So it's an adaptive learning rate schedule. And we also have a learning rate for these inner stochastic gradient descent updates. Before heading into battle and updating these parameters with our subclassification problems, we store a copy of the initial parameters in this old variables equals model.getWeights. So now we're going to sample a new mini data set. In this case, we have, we're just looking at one mini data set per update. You could have variable amounts of these mini data sets, but in our case, we're just using one in this Keras code example. So then we loop through this mini data set. We have our gradient loop with tf.gradient tape as tape. We have the prediction, our forward pass, the loss, which is sparse categorical cross entropy on predicting those 0, 1, 2, 3, 4 labels on these images. Then we have the gradients is the loss with the model, the trainable variables of the model, and then we apply the gradients using our tf gradient tape syntax. So now we're calling the new variables are these new model weights after we've done this step on our mini dataset and optimized towards this fitting these mini dataset labels. And now we're going to perform the stochastic gradient descent update on the original parameters. So we do that with our standard learning rate, our standard stochastic gradient descent update rule, where we have the original parameters plus the gradient times the learning rate. And the current meta step size is our learning rate for these initial parameters as we're looping through this. So once we've finished our inner update, we're now going to the evaluation step. So we set the weights with the new variables and just keep track of this new variables and the old variables thing because we're going to overwrite it again as we go into this evaluation loop. So these are the new variables after we did this meta update, and this is the new initialization for a new task. So now we're evaluating these initial parameters, and the way we're doing this is by sampling a new classification problem, a new set of 5 classes, 5 examples per class, and we're doing the adaptation. We're even in evaluation, we're going to fit this new evaluation data set, because the point of the parameters isn't that they're just good for any task right off the shelf, is that they're fast at learning for this new task. So we want to have them do this learning in order to evaluate that capability of being fast at learning for a new task. So we have our test predictions, we have our test accuracy done by just a number of correct, summing it by the total. And so now we're re-going back to the old weights, and we set the weights to be the old variables. And the old variables were these new variables that came out of this inner step, but we did have this updating where we had new variables with respect to fitting this evaluation set. So that's how we define our training loop, updating the global initialization parameters, and then how we have evaluation loop that doesn't actually update the parameters. We don't have like this SGD updating the initialization in this evaluation loop. As we can see from our training log, the model is getting better at fitting these training labels, and it's also performing better on the new test set and adapting to a new classification problem. Now that we've finished our meta training of these initial parameters, we're going to visualize some of the what was happening during learning it. Remember that we had these arrays of the training and testing that we're storing these inner losses into and our inner accuracies. This is some code. I'm not exactly sure what this is doing, but it's smoothing it out for the sake of having a nice visualization of the training and test losses. And we see that, they have this initial dip, and then they're starting to perform well at updating to this new task, which is a really exciting result. So then what we do is we're going to have a new sample of a new problem, get a mini data set, update it towards this mini data set, and then plot the performance, and then plot some of these predictions and give examples of where it made an incorrect classification, and then just overall showing these examples of this new set of 5 classes and then predictions, inferences on each of these test predictions. To summarize, this Keras code example notebook implements the Reptile approximation to the teacher-student inner-outer loop updates of learning the optimal set of initial parameters for adapting to new classification tasks. I hope you're able to get a sense of this idea of these meta and inner updates. Hopefully you have a better sense of how the Omniglot dataset is structured, and how we have 1,623 characters. They're labeled by the character label, and then there's been 20 different sketches of each of these digits, and that's how they form these few shot classification tasks. And it's a really exciting idea, because the idea of being able to take these new characters and then quickly assign discrete labels and form a new alphabet from these randomly sampled new labels for a set of these characters. So I think it's a really interesting idea of thinking about intelligence and thinking about combining these characters to form new vocabularies. And there's all sorts of exciting research being done on this teacher-student outer inner loop gradient thing. This particular algorithm, Reptile, is avoiding this second order thing where you're not only taking the derivative with respect to the current weights, but also with respect to the change in weights. And the change in weights is this idea of how we're optimizing these initial starting parameters. So, MAML, model agnostic meta-learning, adds a little more complexity to what we're looking at in this Keras code example, the Reptile algorithm. But, it still seems to perform pretty well with Reptile, and it's definitely an interesting area of research, this branch of these outer inner loop gradients. And there's all sorts of interesting research papers that are coming out that are exploring this further, and I highly recommend, getting into this area of research if you're interested.